Hello, everybody. We are on to the fourth podcast of week 4, and I'm actually going to split this one up into 2 podcasts, even though it's all on Faraday's law, just to shorten it up a little bit. You're, of course, welcome to watch them back to back. Now, Faraday is the name of an individual who recognized a situation that electrons and the amount of electrons are proportionate to the amount of a chemical that is reacting, which is really interesting. So what this means is in a reduction half reaction, there's a proportionate amount of electrons gained, and in an oxidation reaction, there's a proportionate amount of electrons lost. Now, how do you compare those portions? Okay, we'll chat. Couple different definitions first, just to make sure that you've got these in the backs of your heads. Current. Now, current, those of you who've taken physics, this might be a little more familiar. Otherwise, honestly, you haven't talked a whole lot about electricity since grade 9. But current, by definition, is about a flow of electrons. And as long as the flow is constantly happening, continuing, we have current. Now, by definition, current is how much charge, the amount that passes through a given point in a certain given interval of time. And that means that by definition, even though we always think of current as measured in amps, technically it's coulombs charge per second. Okay, I want you to keep that coulombs per second in mind. It's going to make a difference in terms of understanding as we get to a new formula how the units actually cancel out. All right, moving on. Electron flow, which again is current, is always in a redox reaction, and this is not new at all, guys, going from the anode to the cathode. Of course, the anode loses electrons. It's where oxidation occurs. Of course, the cathode gains electrons. It's where reduction occurs. Think about the logic of this as we continue on. Now, Faraday then, like I said, looked at the proportionality between the chemical amount and the electron amount. Now, essentially then, the amount, and remember when we say these words amount in chemistry, this is really about the number of moles, right? N as a value. So the amount of a substance, and this can be reacted, this can be produced, but either way, it is directly proportional to the amount of charge. In other words, we're talking about electrons here. Alrighty. Now here, is a new formula. If we had been in class, I would have been saying to you, here's another one that you need to memorize. The good news is, with everything that has come to arise through COVID-19, you don't have to memorize your formulas. You just have to make sure that you have them all written down, can access them, and, well, know when to use them, of course. All right, let's check out what's what in terms of this formula. Okay, so first things first, N, as always, represents moles. Now notice with this N, there's a little E negative that's at the bottom. That's because this specifically is not just amount of anything, but amount of electrons. And no different than any other N that it's measured in mole. But it's very specific to not the chemical, but the electrons. Now, I, which may or may not be familiar to all of you, is represented of current. Now, current is definitely in amps, which is A. But like I said before, you need to have in mind that technically it's coulombs per second. And that's going to help you understand, as I mentioned, how the units actually cancel out. T is what you would expect it to be. T is time. And in this case, time has to be measured in seconds for things to work out. F is something new. F is what allows this proportionality to actually work, and it stands for Faraday's constant. Not anything you have to memorize, guys. Faraday's constant is in your data booklet. It's not one that we have used yet, but it is right here. Okay, so good news is it's a value, a constant that's always there for you, and the units are there too. Hint, hint, it relates to electrons, hence that is part of the units. So keep in mind when we refer to F, this is what we're talking about. Notice the units, coulombs. That's why it's useful to write amps as coulomb per a second instead of just amps. And it's coulombs per moles of electrons. Alrighty. Let's continue and actually consider how this works. Well, if we're focused on amounts of moles, and that's amount of electrons versus of a product or reactant, then ultimately, guys, comparing amounts is stoichiometry. Yay! Stoichiometry. Here we go. Let's start working through it. Alrighty. Notice the question. Focus on what's being asked. What amount of electrons? When you see amount, it relates to N. If it says electrons, it's N of, well, electrons. Now it's saying what amount of electrons flow into a copper cathode. Okay, that's a big hint because what happens at a cathode? At a cathode is reduction. Electrons are gained. This is huge. So you have to understand then, if we are trying to produce a mass of copper, make a mass of copper, that means that from a half reaction perspective, we are producing copper solid. Now, what do you produce copper solid from? If you want, you can go back to the data booklet and look through the sheet. You can also form your own half reaction. But let's refer to this just because it's familiar, okay? And if you find the copper half reaction, which is right here, this is the only one on the entire table that allows you to produce copper solid. And lo and behold, this would happen at the cathode. It's a reduction half reaction. That's the one we need. Okay, like I said, honestly, you could have built this one without the table, but the table's always useful. So it's available to you. If the half reaction is there, why not use it? Alrighty, now here's where things are a little bit different. All this has done is given us a balanced chemical half reaction, which, as we know for stoichiometry, is absolutely a step one. But how do we actually go through it now? The whole goal of the question is eventually to get to a mass of copper solid. Now, that means if we're going to get to mass, we need the molar mass of that copper. Well, that's no big deal. Find it right off of your periodic tables, 63.55 grams per mole. And we're going to need N. Here's an issue. We don't have the number of moles of copper solid at all. So if we don't have N, how are we ever going to get mass? Okay. Here's where the wonderful world of electrons comes into play. There's a lot of information we actually know about the electrons and their movement already. Now, consider what these different units represent. A current of 25.0 amps. That means that I've been given current. I equals 25.0 amps, which, don't forget, is actually coulombs per second. The next thing the question says is 200 seconds. Well, seconds. That's a time. That's what we just got. 200 seconds. I don't have to convert anything. Seconds is what I want. That's super useful. We know something else. Faraday's. That's always there. 9.65 times 10 to the 4 coulombs per mole of electron. So don't lose sight of that. Look at what this comes down to then. Based upon all three of those, I can now use my new formula. Number of, whoops, I want the eraser. Where's that thing? There we go. Okay, number of moles, N, of electrons is equal to the current I times the time divided by Faraday's constant. Start plugging in what you know. Okay, our current, 25.0. Again, I'm going to write this as coulombs per second instead of amps. I'll show you why in a second. Times that time of 200 seconds, all divided by Faraday's. 9.65 times 10 to the 4 coulombs per moles of electrons. Now, I usually put these, because it's in scientific notation, in brackets as well, so that things don't get messed up. Look at the units. Coulombs cancel out, seconds cancel out. Hey, we're left with moles of electrons. That's good news. Okay, work it all out. We're going to end up with number of moles of electrons is equal to 0.0518 moles. All right, here's where the stoichiometry starts to factor in. This N of electrons that I just highlighted is specific to, well, like we just said, electrons. Okay, well, if that's true, then we've got N of electrons equal to 0.0518 moles. How do I then relate that to number of moles of copper? Consider the ratio. If this is 2 compared to 1 in front of the copper, it's a 2-to-1 ratio. From a stoichiometric perspective, I can compare that ratio. Divide by 2 times by 1. You guys can write out the ratio too, however you want to work around it. We end up with half the amount of moles of copper solid as we do of electrons. So, in other words, we're going to have a total now, take that divide by 2, of 0.0259, the number keeps going on my calculator, ... moles. We just figured out what N is. So if now we've got N of copper and molar mass of copper, then we've got enough information to figure out the mass. All right, so formula-wise, M is equal to number of moles times molar mass, number of moles of the copper, of course, which we just figured out was 0.0259 ... moles, times the molar mass of copper that I wrote down before, 63.55 grams per mole. Calculate those out. Our mass of copper, we need 3 sig digs, 1.65 grams. In terms of what's what, honestly, mathematically, it's not that different than things you've done in the past. The key thing is, though, is a new formula where you can now relate the moles of electrons to the current, to the time as well. And then with stoichiometry and a half reaction, life's good. All right, let's try another question. Check out this one. This one puts a little bit of a different spin. We're looking for not the final mass or the initial mass, but the actual mass change. And I want you to do it in terms of grams. And we're going to do that for each electrode. By each electrode, I mean, hey, how is the cathode going to change? And hey, how is the anode going to change? It's very specific here. Now, what are we doing this for? Well, we're going to be focused on a copper aluminum. Notice the change here. This is a voltaic cell, so it's spontaneous, fine. And notice this little key switch as well. It is operating with 500 milliamp current. Your prefixes for conversions are coming into play. Also notice 3 hours. Time with these needs to be in seconds, so there's a whole lot going on here. Okay, this is a voltaic cell. So honestly, before you can do anything else, we got to list all of our different chemicals, because right now you have no idea what's even acting as the cathode or what's acting as the anode. So let's start it out. It's copper and aluminum, so you know that there's going to be copper solid. Fine. Copper solid, if you check out your data booklet, has to be present in a half reaction with copper 2+. So that's the next thing that I need to write down. So copper 2+ ion is there as well. Okay, next thing that's present, aluminum. I write it down. Aluminum solid. Once again, go to your table of half reactions, and as you move your way down, there's our aluminum. Now for aluminum to be present in a half reaction, we also need the aluminum 3+ ion. So that's got to be listed as well. Al 3+ aqueous. Aqueous, aqueous, aqueous. Hence, water is also a factor. Now, guys, we just looked at both of these on here, and it becomes fairly obvious fairly quickly that we're going to have these four possibilities. Well, naturally, the copper 2 plus, since it's there, is the SOA, and naturally the aluminum solid is the SRA. How do I know? Because it says in the question, this is a voltaic cell, which means we have a spontaneous reaction. Okay, so list them. Copper 2 plus, or note them I should say, is the SOA versus aluminum solid is my SRA. Alrighty, what does this mean? This means that we're trying to find out which electrode is gaining and losing, that I have to make sure I correctly identified that SOA as the cathode and that SRA as the anode. We'll get more into that in a moment. First things first, let's play with some givens and some calculations. All right, so if our current is listed as 500 milliamps, you can take that little m and just replace it with a 10 to the negative 3. If you go back to your data booklet, this is where I'm getting this from, guys. Whoa! Here we go. Look at those prefixes, right? A little m is 10 to the negative 3. So I can just replace it as such, right? In other words, then, our current is going to be 500 times 10 to the negative 3 amps. Or another way to put that is 0.500 amps, in other words, coulombs per second. All right. Time-wise, well, it says that it's 3.00 hours. To convert this to seconds, you basically need to use a proportionality. There are 3,600 seconds in an hour. 60 minutes times 60 seconds, 60 times 60, 3,600. So if that's how many seconds are in 1 hour, look mathematically. Hours will cancel out. 3 times 3,600 seconds will be left over. In other words, this is 10,800 seconds. Faraday's we've got, and we always do, so we're good to go for that. And the number of moles of electrons, well, here's our unknown. But if you look at everything that's here, we have more than enough information to now calculate the moles of the electrons. Okay, remember, current times time divided by Faraday's equals 0.500. Again, I'm going to use coulombs per second so things cancel out. My time I converted to seconds, 10,800 seconds, divided by Faraday's constant, 9.65 times 10 to the 4 coulombs per mole. You're going to get a fairly significant long number. Make sure you write the whole thing down because you're going to have to use it again. 0.055958, it keeps going, moles of electrons. All right. Well, this is all good and fine, and it's a moles of electrons, but we need to relate this to moles of my solid metals, my cathode that is going to be producing a solid metal, and my anode that is going to be oxidizing away the metal and turning it into a cation. All right, so remember back. Our SOA, our reduction reaction, is going to be with the copper 2 plus. If I write out that reaction, I'm going to have copper 2 plus aqueous plus 2 electrons will be reducing into copper solid. Okay, that's my cathode, my reduction reaction. So the cathode is going to gain mass. How much mass? Well, that's going to depend on the amount of electrons that were gained. What amount was gained? Oh, lucky us. Well, we calculated already this amount. So that amount of electrons relates directly to these electrons, right? Proportionately, it relates to, of course, the copper solid produced. So I can write that N of electrons right here. 0.0559 keeps on going, of course, moles. Now consider this. This is a 2-to-1 ratio, 2 to 1. So in terms of number of electrons of copper that relates to, well, I'm simply going to have to take that and divide by 2 times by 1. We're going to end up with a number of moles of copper. I'm going to write it below because I'm running out of room. Take that, divide by 2, 0.02797 ... moles. Wow, we have an amount. That's huge because, of course, I know the molar mass of copper right from my periodic table, 63.55 grams per mole. M, mass, is going to be equal to the number of moles times the molar mass, which means that we've got our 0.0279 ... moles times the 63.55 grams per mole. Our moles cancel out. We are now wonderfully left with mass. And mass of the copper is going to increase by 1.78 grams. How do I know that it's increasing? Because we are producing the copper metal. It is a reduction half reaction. When the electrons are gained, copper solid forms at the cathode. So here is the first part of our answer. Mass of copper solid increases. All right, I want you to keep that N value open into your heads. I'm going to erase over here so that I've got room to start to do our half reaction for the aluminum. All right, so moving into this space, the aluminum is going to be at the anode, and we're taking a situation here where aluminum solid is losing electrons to become aluminum 3+ ion. How many electrons? Well, 3 of them. That's the balanced half reaction. So once again, we already know the amount of moles of electrons that were lost. But we also know that this relates to that balanced half reaction of a 3-to-1 ratio. Okay? So my N of electrons here is equal to what I found before, 0.0559 ... moles. I take that and I can relate it to the aluminum solid. So divide by 3 times by 1. When I take that N value and divide by 3, we get a new value, N equal to 0.01865 ... moles. Okay. Molar mass of aluminum right from the periodic table is going to be 26.98 grams per mole. Similar process to what we just did before. Mass is equal to N number of moles times the molar mass. So that's 0.01865 ... moles multiplied by the molar mass of aluminum, 26.98 grams per mole. Notice that our moles cancel out. We'll be left with mass. Yay, that's what we want. Mass of aluminum, 3 sig digs, 0.503 grams. Now in this scenario, we have the aluminum anode being oxidized away to become aluminum 3+ cations. So that means that 0.503 grams is a decrease because it is an oxidation reaction at the anode. Da-da-da-da! There you have it, folks. A decrease at the anode and an increase at the cathode. And here is your introduction to Faraday's law. We have a couple more questions related to this, and I will go over those in the 5th podcast. So at this point, I would say hold off on doing any more questions on your assignment until you've watched podcast 5.